So let me then now ask, is it possible to build an ethical machine? So is it possible to build a robot that could act on the basis of ethical reasoning, to make decisions on the basis of ethical considerations rather than simply doing a task, which is what most robots do at present? Well, a long time ago, well, 10 years ago, I thought it was completely impossible, but I've changed my mind. And I'm going to show you in a sense how I changed my mind. What caused me to realize, come to the view that it is possible to make at least simple ethical machines. Well, the first thing was thinking about simple ethical behaviors. So here, this image here, cartoon, is a kind of thought experiment. So imagine that you are out on the street and you see someone, perhaps a child, not looking where they're going, not paying attention, perhaps peering at their mobile phone. Not that ever happens, of course, these days. You would probably intervene to stop them falling into that hole in the pavement. Now, why is that? Well, it's not just because you're a good person. It's also because you have the cognitive machinery to predict the future. You can anticipate the likelihood of them falling into the hole. You can also predict what might happen if you intervene. And for instance, you might start shouting or waving your arms. And if they didn't pay attention, you might actually try and go and run over and physically intervene. So now that got me thinking, let's imagine it's not you, but a robot. So here's the same situation, except that the robot is now standing in front of the hole, or moving towards the hole in the pavement. Here's the human not looking where they're going. Now, here what I want to do is to illustrate that the robot has, well, I'm simplifying it, 4 next possible actions. And robots, of course, all have to do action selection, just the same that you and I. All animals have to do action selection, and robots are no different. So the robot could choose action A, which is stand still, action B, turn left, C, walk straight ahead, and D, turn to the right. Now, it's easy to see that if the robot chose actions A or B, then the robot would be perfectly safe, but the human would fall in the hole. If the robot chooses action C, then both the robot and the human will fall in the hole. But if the robot chooses action D, then it might intervene. It might interact with the human. There might be a collision, for instance, a gentle collision with the human that causes the human to stop and pay attention and not fall into the hole. So that got me thinking, is it possible to actually build a robot with that kind of ability to predict the future? Well, I wrote down an ethical rule, and this is the ethical rule that expresses that choice, the choice on the previous slide. So if for all robot actions the human is equally safe, then output the safe robot actions. So in other words, just do what is safe for you, the robot, from a robot-centric point of view. Otherwise, output the robot action for the least unsafe human outcome. And you can see, if you go back to this picture, that there is no robot action that leaves the human safe. So, whatever the robot does, A, B, C, or D, the human falls into the hole. Therefore, we are, in fact, talking about the else clause in this if statement. And in fact, the robot action with the least unsafe outcome for the human is D. Because if the robot chose either A, C, or B, something worse would happen to the human than this collision D. And remarkably, this looks like Asimov's first law of robotics. A robot may not injure a human or through inaction, and that's important, that clause, through inaction, allow a human being to come to harm. And so it came to pass that I ended up proposing an architecture for a robot that has Asimovian, if you like, simple Asimovian ethics. And amazingly, the technology to build this robot already exists. It's commonplace. And many of you, I guess, on the course will be using robot simulators. So this is a picture, a screenshot from the simulation tool Weebots. And it's a simulation of robots playing soccer. And you can see that there are 4 robots in the simulation. And you can even see little images on the bottom looking through the cameras, the eyes, if you like, of the individual robots. So robot simulation is a powerful technology. It already exists. We use it routinely to test out ideas in robotics in simulation before then trying them out on the real robot. It's quicker to do that and often less expensive because, of course, if the idea doesn't work, then no physical robots or people indeed have been harmed by using the simulation. But the idea of putting a simulation of a robot inside that robot is very, very difficult. It's not new. I mean, I didn't come up with this idea, the idea of what is called simulation-based internal models, but not many people have done it. It's very hard to do technically, very hard to do technically. But nevertheless, we have achieved it. And this is the only bit of technical that I will give you, well, apart from that little bit of code earlier, or pseudo code. So this is a block diagram of what we call the consequence engine. So the thing to notice is that everything on the right-hand column is a regular robot's control system. So you have sensory input at the top, then you have a robot controller with action selection. That's very important, action selection. And then the selected action is carried out by the robot, which drives the motors. So this is the sense, plan, action loop that I mentioned in my slide earlier. Now, the consequence engine runs completely in parallel to that. So it's a separate process which is not part of the robot's control loop. That's very important. And the consequence engine contains a simulator. So these 3 parts in the middle, the robot controller, which is a copy, an exact copy of the real robot's real controller, the robot controller, the world model, and the robot model. So those 3 parts are the simulator. A simulator always has those 3 components. And the idea is that we initialize the robot model and the world model with the current state of the world using this object tracker localizer. So in other words, we want to make sure the robot's model of the world is correct for right now, for this particular instance. Then what we do is that we loop through that simulator, rerunning the simulation from the point at which you are right now to sometime in the future, typically 10 seconds into the future, for all of the next possible actions that the robot could take next. And in the case of my simple thought experiment, it was 4 next possible actions. And for each of those, then you look at what happened at the end of that simulation run, i.e. 10 seconds into the future typically, and then figure out how that applies to the logic. And in fact, this picture shows a safety logic, but in fact, what we'd actually do in the ethical robot is put an ethical rule. The ethical rule I mentioned earlier would be the logic that goes into there for a simple ethical robot. So we've done this experiment. In fact, the first experiments were in 2014 and using the ePUC robots. And this setup here is more or less the thought experiment that I described to you. So we have this arena, which is, in fact, we're using an old football, robot football arena, but but it's not being used for robot football, as you can guess. So we have this hole in the ground. It's not a real hole, it's a virtual hole, this yellow patch here. The A robot it's an A robot because it's the Asimovian robot. It's the one that is running the consequence engine and is behaving ethically. The H robot is acting as a proxy human and only is programmed with simple obstacle avoidance. It doesn't have any other behavior, certainly doesn't have the internal model that the A robot has. The A robot also has its own objective, and rather confusingly, it's called goal, a goal position. So the A robot is also trying to avoid falling into the hole and is going towards that position. So it has something to do. In other words, the A robot isn't just sitting there waiting, but is actually moving towards its own goal position. So let me show you first the results of this particular experiment. So, and this is the paper that we published back in 2014. So you'll see initially the H robot, which is right there, and you can see the A robot starts to move, then notices the H robot, and there's a gentle collision. The H robot is heading off safely, and the A robot doesn't fall into the hole and goes to its target position. And you can see we've speeded this up 4 times, 16 times, and 64 times. So you can see, I think, quite easily that it works. The consequence engine, and I should also explain a little bit of technical for those of you interested. The consequence engine is running twice every second. And for each of those half-second cycles, the consequence engine is actually simulating not 4, but 30 next possible actions. And for each of those next possible actions, it's simulating 10 seconds into the future. So that means every half a second of real time, we're actually simulating 300 seconds of potential future. So it really is possible, and this is, we're not using any supercomputer. It's simply running on a laptop, a regular laptop computer connected over the Wi-Fi network with the ePUC robot. So it's not computationally intractable, which is really obviously really important. This technique wouldn't work if it required immense computation. Now, when I recall when we were drafting the paper with Christian and my postdoc Wengu, I said to them, look, I said, this is a bit boring because, we've built this thing and it works, but it's not particularly interesting really just to say, look, here's a thing, we built it and it works actually very well. I suggested then that we add a second human. So let's give the Asimovian ethical robot a dilemma, and I'll show you what happens. And this is, we believe, the world's first example of an ethical robot facing an ethical dilemma, at least experimentally. So here we have 2 proxy humans, both heading towards the hole. Now observe that the A robot initially goes towards that one and then turns round and goes to this one, and oh dear, both the H robots fall into the hole. A robot is fine, but both H robots go into the hole in the ground. So this is clearly not working as well as we had before. And there you see that the A robot saves one of them, but often doesn't save either of them. I mean, sometimes the robots, the H robots, don't actually go into the hole anyway because they're just pointing in the wrong direction. They set off randomly within a cone of directions to start with. So so it was really, I'm just running that again. It was really puzzling to us as to why the A robot wasn't saving one of them every time, because we know it can. And it's this dithering that is the reason. Essentially, we realized that The problem is that our A robot has the opportunity to change its decision, to change its mind, because it doesn't have a mind, but to change its decision every half a second. So that means that the robot is effectively indecisive. It's a little bit like, imagine that you're out at the park and you see two children rushing towards a lake, and it's unsafe, and you want to save them. And if you run towards one of the children, then change your mind and run towards the other one, and then change your mind again, if you do that, it's unlikely you'll save either of them. So being indecisive in this kind of real-time ethical problem is itself a problem. And we realized that there needs to be an additional mechanism so that ethical decisions are, if you like, a little bit sticky. So ethical decisions have a half-life, that they're not simply superseded in the next cycle. And we think that would improve the performance of this ethical robot. But it was nevertheless extremely interesting, and the paper that we published, ended up creating a bit of a fuss, both in the media and among the academic community, and it's been very widely cited now, this particular paper, largely because of the ethical dilemma, not so much because of the architecture. But we tested the same architecture in 2018 with these Now robots. Here, the blue robot is the ethical one. The red one is the proxy human. The blue robot is heading towards this pillar here. The red one has a danger zone over to the top right. You can see that the blue robot did stop the red robot from heading toward danger. It also made it to its own destination. This is all described in this paper. And here we see the same ethical dilemma we saw before, but you can see that the blue robot, the ethical robot, initially heads towards this guy, but then changes its mind and heads towards this guy. So the interesting thing here is that it verifies that it's this ability to change its decision that is causing the ethical robot to fail to save both of the robots, if indeed it could. It's worth noting that in fact in the EPUC experiment, very occasionally, perhaps twice out of 30 something runs, the ethical robot did manage to save both of the proxy humans. So how ethical is our ethical robot? Well, not very, of course, is the short answer, but it certainly does qualify as an ethical robot. It implements a very simple form of consequentialist ethics. But the important thing to understand, of course, is that the robot behaves ethically, not because it chooses to, but because it's been programmed to do so. So it's kind of, it's like an ethical zombie. It cannot choose its ethics. It can't choose to be unethical, but it behaves ethically simply because it's hard-coded to behave ethically. And of course, we've hard-coded the rules in the robot. So one of the benefits of this internal simulation-based internal model is that we know exactly what's going on in the robot's brain. Again, I'm putting quotes around that because I mean that only metaphorically. So we can look inside the robot and find out exactly what's going on during its decision-making process. Now, we think that is really powerful because it means that if something goes wrong, then you can find out exactly why. Again, as part of our accident investigation work, Marina and I proposed some years ago that all robots should be fitted as standard with the robot equivalent of a flight data recorder. In other words, well, we call it an ethical black box. So these of course are fitted as standard, as you know, in all aircraft. It's a fundamental requirement of commercial. Well, in fact, all aircraft have to be fitted by law with these data recorders. We think that robots should also be fitted with data recorders, not just ethical robots, but all robots. We think it's absolutely fundamental. Otherwise, you simply cannot investigate accidents after the event. And again, I could give a whole lecture on robot accident investigation, and indeed we have a new paper on robot accident investigation, which is on arXiv. If you're interested, I can send you a list of all of the relevant papers afterwards, if you like, if you would like to see them. And yes, the project that we're working on, it's a 5-year EPSRC funded project called RoboTips, Responsible Robots for the Digital Economy. If you're interested in that particular work. So just to finish my segment and indeed the lecture, one of the things I realized when we built these simple ethical robots is that we don't need a major breakthrough in artificial intelligence to build an ethical robot. In other words, we don't need to wait until we can build a robot like Data in Star Trek. We can even, I mean, they're very minimally ethical, but nevertheless, we can build simple ethical robots. Now, actually, there's a different question. If we can build robots, that's okay. We've shown it in the lab, ethical robots. Question though remains, should we build ethical robots? Is it ethical to build ethical robots? That again is a subject of a whole another lecture. Perhaps we can talk about it in the Q&A. But in fact, again, if you're interested in machine ethics, myself and my colleagues, Katina Michael, Jeremy Pitt, and Vanessa Avers, prepared and published a special issue. We edited and published a special issue of the proceedings of the IEEE on machine ethics, which focuses both on the design and the governance, the ethical governance of ethical AI and autonomous systems. And the editorial paper, which is called The Design and Governance of Ethical AI and Autonomous Systems, explores all of these questions of ethical governance, the question of whether you should build ethical machines, even if you can. So that brings me to the end. All I need to do is to thank my colleagues who all contributed to the work I presented and the papers that I've referred to here. So we certainly need standards, regulation, and ethical governance. We need ethically aligned robots. And then when we're talking about machine ethics, we need to debate the question, to what extent at all, even at all, should we delegate ethical responsibility to robots? And underpinning all of that, we need transparency. So at that point, I'll stop and say thank you very much indeed for listening.